you.
Thank you. Thank you, Dengson, for having me here. The reason I joined early was I wanted to hear Felix because I'm a big fan of his work. So you guys
Yeah,
should stick
we'll
around for
do
that
his presentation later for sure.
as well. When we think about light sources for vision or even graphics, we think about light sources as illuminating the scene, right? That's what we think about light sources. But light sources themselves are pretty fascinating, right? You think about natural sources such as the sun and the sky and the stars and so on, but also artificial man-made sources, right? So your bulbs in your home, street lamps, sparkles, and other kinds of things, right? And I want to expand this notion of a light source to also materials that reflect light really, really well. For example, retroreflective markers, for example, right? Or snow, for example, right? So all of the light just gets reflected back, and you can sort of think of them as light sources themselves. And so in this talk, what I want to do is to give you guys a few examples of what I mean by light sources as scenes, and what can we recover from the light sources, observation of the light source itself. Okay, so going back to Jean-Francois Lalonde's thesis, really cool thesis. What he did was he was looking at images of the sky. There could be the sun or not. And by just looking at the brightness pattern of the sky, so here's the sky is the light source, right? He could estimate the orientation and the zoom of the camera with respect to the sun, right? In other words, the sky itself became like a calibration target. Instead of a checkerboard, you have the sky as a calibration target. And what he did was, with this kind of an idea, he could actually calibrate cameras all over the world, right? This calibration was pretty accurate, surprisingly, with a few percent error in terms of angle as well as focal length, right? And so this is an example, as I said, the light source itself is acting like a scene and it's giving you some useful information. Another example, if you think about at night, so imagine you're walking down the street, you're looking at a street lamp and it's very misty, and you see the glow around the light source, right? So the light gets scattered from the source by the atmosphere or the weather before it comes to the camera, right? And by modeling how the light sort of glows around these light sources, one of the things that I did in my thesis long time ago was to be able to estimate the visibility of that line of sight, right? So you can actually say it's 2 miles visibility or 1 mile visibility and so on by just looking at the light source and the glow around it. But not only that, you can actually, it turns out that you can estimate the type of weather. You can actually say it's mist or rain or fog or rain or snow and things like that, right? So this is an example where the light source is immersed in the atmosphere in a medium, and you're getting information about the atmosphere itself, right? And so you can extend this one step further and say, hey, why limit to just atmosphere, but we can immerse light sources in other media, for example, ocean waters. So hopefully you can get impurity levels in ocean waters by immersing light sources. And we went sort of crazy, and we immersed light sources in all kinds of media, including juices and wines and beers and everything else, right? And coffees. And it was kind of strange project, but it was a lot of fun because we could now estimate the scattering and absorption properties of all of these media by just watching the light source itself, right? So we had a physics-based model, and we were using the image and then estimating the properties in an inverse manner, right? And the nice thing about that is that now in the movie industry, it's very commonly they use the parameters that we estimated there to render wine glasses and glasses with Coke and coffee and things like that. And the latest I heard was one of the special effect houses was rendering a river made of beer. I don't know why that is, but that's what you can do with these kinds of things, right? So this is another example of what you can recover by observing light sources. Another example I think I want to mention is this was from a very early piece of work in ICCV to 1999, where we were looking at light sources on a clear night and a foggy night, and the attenuation would tell you the relative distance of the light sources from the camera, right? So how far is one street lamp with respect to another one? That could be computed using the attenuation model, right? So this is yet another example of looking at a light source and getting information about the scene. The next example is one of my favorite, but it's not my work, but it's from my postdoc, current postdoc, Mark Scheinen, and his co-authors, Yoav Schechner and Kiros Kotlakos. This was one of the best papers a few years ago in CVPR. So what they did was they were capturing, very cleverly, they were capturing the flicker of light sources, right? So because of AC, alternating current, light sources flicker, right? And the phase of that flicker tells you what phase they are on. And so here's a beautiful visualization of that flicker in an entire city. And you can actually tell what phase each bulb is on, 0, 120, 240, and 1/3 of the bulbs are on one phase and so on, right? And this is a really good example of analyzing, let's say, the electrical grid by just looking at light sources, right? So the last example I want to give before I go into today's talk a little bit is the work we did with smart headlights. And when I was young, I was a fan of Star Trek. I don't know how many of you were fans of Star Trek. And I really loved the captain saying, "Engage." And they would just show the, this vehicle moving forward, spaceship moving forward, and all the stars whiz past you, right? But as I grew up, I figured out how far these stars are and the speed of light, and it made no sense to create these kinds of images. But what you would see is the same effect as you would be driving in snow, for example. If you're driving at night and in snow, and all the snowflakes come straight towards you, just looks like that. And that's what this reminded me of. And in fact, we had a big project about building smart headlights that can help you see through snow and rain, gives much better visibility to the driver. Here, these snowflakes are acting like light sources. They are reflecting the headlight so well that they might as well be light sources themselves, right? And by streaming light in between these snowflakes, you're able to reduce the visibility of snow and therefore increase the visibility of the scene itself, right? And so these are some of the examples where I'm saying, hey, it's interesting to look at light sources as scenes themselves and not just as a mechanism to illuminate a scene, right? And so today I want to just talk a little bit about some more recent work on how to capture these light sources that are bright, sparse specks in the image, but move very, very fast, right? So examples of these are in motion capture. So you have retroreflective markers, and there could be very fast motion. In particle image velocimetry, you have lots of particles that are reflecting light and they're moving really fast, as well as crazy examples like combustible particles. You know, if you look at fireworks, you see all these combustible particles that are moving very fast. How do we capture these kinds of scenes where you have bright, sparse specks, right? So if you look at any of these things, they are sparse. They occupy really a small part of the imaging plane, right? And we want to be able to capture these things at high speed. Okay, one possible way is to take your camera, let's say this IDS camera, which is rated for 120 frames per second at full resolution, and you capture that, but that's the only speed that you get. But what you could do is you could reduce the region of interest here, right? So if you reduce the region of interest, your frame rate increases. So in this case, the frame rate increased to 2000 frames per second, right? But the problem is you're not able to see all the light sources that are not in this field of view, right? So you're reducing the field of view significantly. And so just region of interest is not going to give you the solution that you want here, right? Another interesting possibility is you guys may have heard of event cameras. This has become very popular, right? A dynamic vision sensor. So it just measures the changes in brightness. And so hopefully just by transferring the changes in brightness, it has more bandwidth and therefore higher speed. One of the problems with these kinds of sensors is that they are really poor spatial resolution. That's because you have to have electronics with these pixels, and they have low fill factors as well, right? And so even if you did everything well, the speed at which these things can transfer is not very high, as opposed to, for example, a rolling shutter speed that is very, very fast, right? And so instead of thinking about these two ways of solving this problem, what we want to do is to look at the scene, but we want to make sure that this light somehow hits the sensor that we want to use, right? So if we just use a 2D sensor, it needs to cover the whole field of view. But if you want to just use a small rolling shutter, just one row or just a small ROI, we want to make sure that all this light somehow is spread such that it is guaranteed to hit this sensor, right? And so if you're able to capture some part of the light from every source on the sensor, then our job is done, right? Or at least half done. From that, you can sort of decode the 2D positions. So think of a 1D camera that's going to give you a 2D image, right? And the nice thing about this is that 1D cameras are blazing fast, right? And so you're able to capture very high speed videos using these kinds of systems. So how do we spread this light out, right? Remember, I'm talking about light sources. These light sources are bright, and so you can try to spread these light sources out. And so one solution is to use what's known as a diffraction grating. It just looks like a complex thing, but it's actually something very simple. In fact, most of you might have used this to produce artistic effects. You can buy this in any store. You can fit it in front of your camera, and all these headlights, create these beautiful streaks, right? And this is called a diffraction grating. It just takes the light source and then spreads it into a star shape, for example. And there could be any number of these diffraction gratings that produce different kinds of point split functions, okay? And so imagine putting your 1D sensor somewhere in this 2D area. As long as you capture some light from every light source, you are capturing all the light sources, right? And so these diffraction gratings are not just for fun, but they're used for a lot of scientific applications as well. Okay, so you can use one of these diffraction gratings, and just like a prism, these diffraction gratings just spread the light, the spectra in different directions. Okay, and so what you do is you take your line sensor, just a 1D sensor, and you place it somewhere, and these light sources that are there everywhere else just get spread by the diffraction grating, okay, and hit the 1D sensor at different locations. And what we showed was by just looking at the spectrum that you measure, you can directly decode the XY positions of these light sources, right? It's a very, very simple algorithm. We know how the light gets spread by the diffraction grating. It's a calibration problem. Once you do that, you have a way to recover the 2D position. So now you have a 1D sensor that's able to decode 2D positions, right? And so, as I said, it can be done very fast. So here's a fan, and we attached a couple of LEDs, and it's going pretty fast. And the green cross here is showing how our 1D, or a small ROI at 2,200 frames per second is capturing that rotation of that fan, right? And this is just nearly a 1D sensor, right? And of course, you can put this outside. Again, very low light situation, but you can track light sources at very high speed, all the cars coming at you. You could be driving at high speed and all the street lamps could be whizzing past you and you could be tracking all of them really well, right? So another thing that you could do with this is instead of just thinking about point sources, you could also be thinking about line projection or line sources. And this reminds us of structured light 3D. And so instead of shining just one point, you could be shining a sheet of light and you have the intersection. If you can see my mouse, you can see the intersection becomes very bright, right? So that's standard structured light. And so you can use the same diffraction grating principle with a 1D camera, and the diffraction grating just spreads out the light as shown in this image here. And if you're just capturing one slice of this thing, you're able to then decode what this line looks like in 2D, right? And so what this allows you to do is to do structured light 3D reconstruction with a 1D sensor and a 1D light source. And that's the first time somebody has done this. Usually you need a 2D camera and a 1D source. But here you can do this with just a 1D source and a 1D sensor. So here's your line sensor, and this is the diffraction video. The only thing you capture is just this lines in the middle, right? So let me just play that video again. And this is the 1D measurements that you get on the right. And after that, you can run your structured light method and you can get 3D reconstruction, right? And as I said, this is the important distinction here is that you can do this with a 1D sensor and a 1D source. And what that allows you to do is to scan things at extremely high rates with very fast conveyor belts. Usually these kinds of systems have high-speed 2D cameras that are very expensive, and you can replace them with just 1D sensors, or use your rolling shutter of your 30 frames per second camera, okay? Now, moving on, these things work when the light sources or the sources are really sparse. But what happens if they become dense? So if you think about particle image velocimetry, you put a bunch of particles in liquid and you stir it really fast, right? And you want to see the motion of that liquid by watching and tracking the particles. The problem there is that these particles are too dense. And so the image that you capture in a 2D plane would be really, really dense. And so you would get a combination of different colors and you could get mixtures, and that would not be easily solvable to decode the 2D position as before, right? And so in general, it doesn't work if you just had a 1D sensor, right? And so instead of that, what you can do in your camera, most cameras allow this, is to specify a few ROIs, right? So if you just, instead of one ROI with one 1D line, you can specify 8 of them. And this is something that is done very commonly in all machine vision cameras. And not only that, it could be any arbitrary sensor sampling, right? So if you have a sampling on your 2D plane, sensor plane, as long as you get high frame rate, because you're capturing very few pixels, you can still use this kind of a method, right? And so another thing that we did was, instead of just having a diffraction grating with just a spread in one direction, you could create an arbitrary diffraction grating. So you can buy your favorite star filter and you can put it in front of your camera, right? And then what it does is that you create a convolution of the original unknown image with this known point spread function, right? And that's what you get here. You finally subsample it according to your sensor sampling, and that's the only thing that you measure. And as I said, you can specify sensor ROIs here, right? And so you would be measuring only a small fraction of your 2D image plane, and therefore it could be really fast, okay? And so now the question is, how do we deconvolve this from a sparse set of measurements? And that's a well-known optimization problem. You have the unknown image in 2D, you have some point spread function that you know, you have a sparsity, sparse sampling on that image, and then you have a sparsities prior, right? So this is a vanilla optimization function. You can just use existing code available, and you decode the 2D positions, right? And so you can do this for multiple different spectra of sources. So what if there could be LEDs of different colors? All you would have to do is to add up contributions of each of these LEDs. And so if you look at the diffraction grating here, for each source, you would have a different point spread function. And as long as you've calibrated these different point spread functions, solving this inverse problem is pretty straightforward. You just add another sigma 1 to k, where these denote the different spectra of the sources, right? And so you can, in fact, estimate the type of source, the spectra of source from this optimization problem, okay? And so let me show you a few results here. And I'm going to show you high-speed videos that we have captured with just ordinary 30 frames per second cameras by just using these ROIs, right? So I'll talk about different kinds of reflective markers, retroreflective markers that you could use that just make it look like they are light sources, right? They're bright and they're sparse. And so here's a video of a Nerf gun. And we have put a bunch of retroreflective markers on the bullets as well as the gun. And it's spitting out 5 darts per second, right? It's pretty high speed. And so move this, oops. And then that captures a video, and then you decode that video to produce the video, 2D video that you see on the right here. And because we can do high speed from just 30 frames per second videos, now this is 1,000 frames per second video, right? Another example is motion capture, human motion capture. So here, Mark Scheinen is doing this really tough jump rope. You have to go through twice. The rope goes through twice for each jump. And it's a pretty tough thing to do. I don't know how to do it, but maybe some of you do. And so you can capture just a few ROIs and then recover the full 2D. And I'm going to show you just this video. On the right is the full 2D that is recovered. And this is the slow motion video, right? So it's an ordinary 30 frames per second camera, but it can capture these sparse sources, if you will, at very high speed. And as you can see that the rope is going twice beneath his feet for each jump. And you can do this for other kinds of markers. So I'm just going to show you this video.
Here's the recovered 1000 FPS video of the markers. Notice again that the actor is swinging the rope 2 times under his feet for every jump. This is a fast exercise that doesn't always go well.
So you can do motion capture pretty well with cheap 1D sensors. That's the take home of this. You can also do particle image velocimetry at very high speeds. So this is 3000 RPMs. You stir the liquid and the particles flow with the liquid, right? And your imaging system, you can see the diffraction grating here. You have the fluid here. The imaging system is capturing that at 30 frames per second, but you're doing it with a camera that is rated for 30 frames per second, but you're using ROIs, right? Here we're using 8 ROIs. And from that, you can recover the 2D position of all these particles at 1000 frames per second. The final example I want to show is this sparkler. This is pretty hard. In fact, I've seen some high-speed videos of sparklers even at 20,000 hertz. It is very hard to capture them, right? And so this is just a 30 frames per second video of the sparkler, right? And if I want to see the individual sparkles that go, that would not be possible with this system, right? And so by introducing a diffraction grating in front, you're able to capture, as is shown on the right here, is small sparkles that are falling and expanding. And as you can see, the sparkle falls on the floor and then rebounds, right? All of that you can do because you're capturing things at high speed, but sparsely, right? So with that, I just want to quickly summarize to say that light sources themselves are fascinating. They should not just be thought of as ways to illuminate the scene. There are lots and lots of applications where it's beneficial to look at the light source and recover something about the scene. And hopefully I showed you a few of these examples to get you interested in these kinds of applications. So with that, I thank all my students and collaborators who helped me with all of these projects over the years, and I'm happy to take questions. Thank you.
Yes, thank you. Thank you very much for your excellent talk. It's so great to see such unique research. I mean, it's very focused and goes so deep. So yeah, it's great. So are there any questions from the audience?
There is already a question by Vin on the.
Yeah, I think so. That's a good question, Wim. If you, in fact, there was a previous paper that used cylindrical lenses. The problem with cylindrical lenses, you would definitely need 2 of them and 2 cameras. And this is another thing that we showed in our paper as well, right? If you wanted to do with just 1 camera, then you would have to modulate the light source. Otherwise, you would not be able to estimate both X and Y coordinates.
Mm-hmm. Yeah.
Okay, thank you.
Yeah,
Also, this research seems related to compressive sensing, right? So can you maybe discuss what the relationship is?
Compressive sensing is it's a broad field where you're subsampling, you're sensing far fewer, right, than the actual things that you want to estimate, right? And so in that sense, we are also solving a similar optimization problem with a sparsity prior, right? So you can think of this as exactly compressive sensing. It's just that you can use readily available ways to do compressive sensing by using ROIs or rolling shutter rather than using a complex DMD system that averages all the values, right? In compressive sensing, typically what they do is they take some linear combination of everything and then they store that. And that makes it somewhat harder for very sparse things. And so in this particular case, the inverse problem is easier because we have a better way of capturing this data.
Yeah. It's so interesting to see that we can turn this lighting source into a very, useful signal. I normally at nighttime, for instance, when we nighttime driving, that this lighting source sometimes, most time, it actually just contaminates our image. So it's great if we can really track and detect them. So do you think that we can actually, let's say, positions many of these LEDs like unique light structures so that we can localize our vehicle phones at night time?
Yeah, I think this is something that I think there was some work before that did it with just 2D images, right? Mm-hmm. And so doing structure from motion or SLAM with just light sources is quite feasible, and it has been shown already, right? Okay. What we want to bring to the table, at least here, is to say, can I capture that at very high speed, and therefore perhaps your accuracy of these light source position estimates may be better, right? And this is something that is still yet to be shown, but my hope is that having this kind of an imaging system on a car, on a fast moving car, will allow you to localize sources. If you think about all the street lamps that are fixed and the car is moving, you can compute the relative position very accurately at high speed.
Yeah. That's great. Yeah. It might be also useful for high-speed train at nighttime or other type of vehicle, not only for the autonomous driving, but also for other type of vehicle.
Yeah, any light source, right? Yeah. Any light source. It could be on the vehicle, it could be other vehicles, it could be street lamps, it could be building lights, could be anything.
There's another question from the chat. So for a very recent camera that is able to capture 60 frames per second and 4K resolution, is it possible to get 60 times 4,000 frames per second with a single line sampling?
So in theory, yes. I mean, what you have to think about when you're capturing images is that there is a fixed bandwidth, right? So the spatial resolution multiplied by frame rate is the bandwidth. It's the amount of data that you can capture and store and transmit, right? And so that product is constant. And so by reducing the resolution, you increase the frame rate. Now, to the extreme case, if you just had one row, you can increase the frame rate by the number of rows, right? And that's probably what you're trying to suggest there. And that's possible for many cameras, but it's usually limited by the design in the sensor, right? So some camera manufacturers, the way they design the ROIs, they have some overhead time for setting registers and resetting signals and so on. So it's not quite that you can get the exact multiple, but it's pretty close.